Good afternoon to everyone. I hope you have a very nice lunch. And for this session, it's a pleasure for me to introduce you to Raffaella Morganti from the Netherlands Institute of Astronomy, Radioastronomy, and the Captain Institute of Groningen. Uh, I think it's impossible to talk about radioastronomy and AGNs, active galactic nuclei, without mentioning Raffaella Morganti. She is one of the leading researchers in the field, and it's really nice to have she here. She will teach us about radioastronomy and AGNs and different techniques employed in this area. Raffaella got her PhD degree in Bologna, Italy, in late 80s, and then she did a lot of postdocs. She was an ESO fellow, moved to Spain in the Canary Islands, if it's in Spain, and then went back to Bologna to work in astronomy as a staff in Bologna, and then went to the Netherlands to work as a staff astronomer. So thank you very much, Rafaela, for accepting the invitation here, and we are very happy for your talk.
Thank you. Is it on? Yeah. Thank you. Yeah. Now I have a task now to accomplish. Well, thanks for the invitation. Of course, it's really very nice. It's a different country, different audience, different style. So it's yeah, it's interesting very. So I'm going to tell you about in this fourth lesson AGN, that I know not everybody is familiar with, so we'll step back. But AGN at radio wavelength. So I know you are also not familiar with radio astronomy. I don't know, blank. So you are not familiar with radio astronomy. So I will also step back and tell you about this. So let me just, like Carlos did, introduce myself just for a minute. So indeed, I'm originally from Bologna, Italy. This is very useful in this country because my Portuguese is zero, but Spanish, okay. So, and I moved to the Netherlands more than 20 years ago. So I'm almost Dutch. And I'm supervising, or I've supervised many students. I really like supervised students. I don't like so much teaching, but I like supervising students. And so please, if you have a question, there is no stupid question we have established, no? So please come to me afterwards if you don't dare to ask during this. And I'm indeed part of the senior astronomy at Astrom, and affiliated as a professor at the Captain Institute. And I'm afraid I have only a website, no social media. For me, I'm a bit old-fashioned, but okay. So, and I've had the luck to receive this ERC grant a few years back that has been really a boost for my research that I will also show you here. And in addition to know about what we do in a project like this, as Carlo mentioned, you know, you have to have all the key questions in place. You also have to have a nice acronym. That's really a key point in a grant. So my acronym was Radio Life, that already summarizes what I'm doing. And also about my science. So first of all, I have a part, technical part in radio telescopes that you will hear later today. And then I'm also working on radio AGN, in particular the interaction of the radio plasma with the medium around and the implication for galaxy evolution. So even if you don't work on AGN, I hope to give you some input on how the AGN can connect to the galaxy evolution, or what you should look for. Okay, so as you have seen in these four lectures, I thought to plan them in a way that the first two will be more general. So today is the radio part, radio astronomy, radio survey, because even if you are not a radio astronomer, in your life you will encounter maybe the use of radio or can be useful, or you should know about the possibility that offers to you. Um, and there is a lot out there and is growing, and I think it's the right time to keep an eye on that. Used to be really a black magic kind of art, but now is getting more open to everybody. And tomorrow I want to tell you about AGN, uh, taking also a step back, not only the radio part. So starting from the basic, I hope not to bore you too much. And then the final two lesson will be more on the work that I do, the two stream that I do in my research, how the AGN go through a life cycle, let's say, on and off, and why this is at all interesting, and the impact of jet on the medium. Okay, so, and I also, every now and then I put a break. If you have a question, please ask. No need to wait until the end. Okay, so radio astronomy. So, well, this is my starting point. This is what you would see, you may see, if you would have a radio eye, meaning that the background image is one of the deep field or one optical image, whatever color doesn't matter, but the purple stuff is the emission from a radio galaxy. That is the one that we will see in more detail tomorrow. So this is these are relativistic electrons and magnetic field that emit this emission that you detect with the radio telescope. So as you can see immediately, I mean, this is of course a spectacular object, and I'm trying to keep you awake and to keep you interested. This is Hercules A is really a beautiful radio galaxy. But the idea here is, anyway, you have a galaxy in the middle, star, 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 all your nice galaxy. Yeah, should use this. So you have a galaxy in the middle, all your stars that you love so much. But then you see the radio emission, first of all, doesn't follow the stars, the emission of the stars, but also can be huge, goes well beyond the stellar object. So it's telling you something completely different, and this is what I would like to show you. So, although you are all young and you don't care about history, anyway, I put at least one slide about how radio astronomy came about, because in a way it's really by accident. So this is something that Karl Jansky in the 30s, yeah, was doing for completely different reason, really telecommunication. This is the base of radio astronomy. So looking for some very annoying noise that they had in this telecommunication first try. And they could not identify this noise, and the genius of this guy, Karl Jansky, was to see that this noise was moving with a certain time, I mean 4 minutes, and so he managed to identify the noise with actually the center of the galaxy. So then making the connection between the universe and the emission in the radio, because indeed the radio was the first wavelength study which astronomy opened up after the optical. The optical we all know, you know, Galileo, the telescope, blah, blah, blah. But the radio was the first window in addition to that showed that the universe can really emit a different wavelength that we don't see with our eyes. And then the X-ray came and all the rest. And so this was done very early. But then essentially radio astronomy started after the Second World War. Well, both for obvious reasons when the research restarted, but also because they recycle a lot of war radar. So you see one here that was in the Netherlands, and this was a German rather, that they refurbish and they start looking for the emission from our galaxy. So this is actually the first image of the neutral hydrogen, map of the neutral hydrogen of our Milky Way, made by Oort, that in the Netherlands is, of course, one of the father of everything. Um, but really a new way to look at the sky, because of course it's not so affected by dust and all this, so gives you really a different view. And so if you in some publication that you look at and you see radio data and you see this unit Jansky is just the flux unit used in radio astronomy, of course, because it's a role, essential role. So this is a bit of a complicated, but this you will see, you will see very often, not in this presentation, but in general, if you look at the radio. And so this is you see here the transparency of our atmosphere to different wavelengths here. And you see the radio, well, here is the optical, your optical telescope, and this is the radio, the other wavelength, where you really can observe from the ground the sky and detect the emission. All the rest, you have to go higher up, as high as you can. Actually, for the radio, when you get to the frequency of many gigahertz, that would be the frequency covered by ALMA, you need to go higher up, because part of the atmosphere absorb your signal, and certainly if it's bad weather and all. But for the standard radio frequency that are in this range from few gigahertz to few megahertz, as you will see, you can do from the ground. And so I'll go in more detail later about the telescope that allowed you to do this, but just quickly to show that you have your radio wavelength that indeed goes, if you look here, from few centimeter, few millimeter, if you go to ALMA, few centimeter to meter waves, as you will see if you go to LOFAR, as I will show you. You can, you can observe in the entire range, and I hope to explain you or to, to make clear also why you need this wide range and what tells you. And you have plenty of radio telescope. These are all the names of cryptic for the moment, but I hope to clarify in a moment, of radio telescope that allowed you to do this. And in this range, you can do two types of observation, a bit like in the optical. You can do the continuum, can study the continuum emission of your radio source, if any, or you can study lines that go from the classic H1, that is 21 centimeter, the one that Oort explored for our galaxy, to the other molecule that more or less common, or the one, the CO that ALMA does. So there is a variety of possibility. So nice, but radio has and has had certainly a major limitation, that is the angular resolution. So essentially the angular resolution goes with lambda proportional. Lambda of your observation divided by the diameter of your telescope, at least at this frequency. Then, of course, if you are in the optical, you have also the atmosphere, but for radio, this is the formula. And so, if you start putting, as I try in this table, just to clarify, the typical radio wavelength, so you go for the 21 centimeter, that is 1.4 gigahertz, where you have, for example, the H1, but also the continuum, or you go to higher frequency, like the one of ALMA, more than 100 gigahertz. So if you have this frequency that corresponds to this wavelength, and you put here in this formula, you will discover, very sad, that if you have just a dish, a nice parabola like the reader that after the war they left you, and the the only resolution that you can obtain is very very poor. So we are talking about 100 a second for a 100-meter dish that is one of the largest. Nowadays, the largest one dish is the FAST telescope in China, 500-meter, non-steerable dish. It's just a big bucket there between some hills. So so that's a nice 500 meter, but doesn't take you to the resolution that are interesting if you want to compare with other wavelengths, because that's the final goal. What do I do with the lousy radio image? So, so essentially the idea was if you want to get to 1 second resolution at typical radio frequency, essentially you need a dish of 20 kilometers. That's tend to be very difficult to do. So, so that's where part of my story about radio really started, because until the resolution that the radio observation could reach became close to the one of the optical telescope, radio was nice, but well, okay. For something is interesting, large spiral galaxy, if you study the H1, that's very good. But for all the rest, certainly AGN or small object, there was a major limitation. And so, so I have now a part about how a radio telescope now works. The single dish is okay, you have an antenna and you observe. Looks very much like an optical telescope. But these are fewer and fewer. As I say, the largest one is fast, but you don't manage to get much larger than that, 500 meter, although they are trying, but okay. So the trick of radio astronomy that didn't really make radio astronomy much more interesting was to replace your single dish, yeah, antenna like telecommunication. No? You have the radiation from the sky and the focus of your dish. Replace your single dish with many small telescopes, many. Then you could put wherever you want, as you will see in a moment, and then you connect them. That I think was really the turning point of radio astronomy, and this is, in a way, is great, because this is how you get the beautiful image that you can compare with the optical, although comes at cost of some extra complication in the analysis of the data. Yeah, that is always a drawback. And so that also scared many people away from radio astronomy, I have to say. So radio astronomy was seen as, okay, you do some magic, there are 20 people in the world, they do a lot of magic and they get a radio image. So we are trying to get away from this, but yeah, take some effort. So this is the idea. You have instead of a big dish, you have many small dish, and you connect 2 by 2. This is the interferometer. All the dish, of course, point to the same object in the sky, and then you connect, you correlate. There is a big computer here that combines the data from a pair of telescope, 2 by 2, for your entire array, and we will see what kind of telescope you have, what kind of array. They combine after compensating for the delay, because you are looking in a certain direction, so the signal comes at different time at one telescope than at the other. So this correlator, that is the key point of a radio telescope, the key machine, compensate for this delay, very, very accurate, and then combines the signal. So this is just in some more detail. Of course, I will spare you a lot of detail that really I'm happy to leave to the engineer, but some I need to give you some basic of how it works, because that create the complication, or is something that you should consider when you plan observation or even think about doing radio observation. So, so again, I've repeated here, all the antenna, how many you have is up to your budget, and we will see different type of radio telescope depending on the budget that different people have. And so they point all into the same direction, but as you see, the wavefront will reach one telescope before the other, so you, as I said, you compensate. And then you correlate, you combine, let's say, forget about the word correlate, you really combine, multiply the two signals for each pair of telescope, okay? So what you get here is the resulting signal that is essentially like an interferometer. So it's not your direct measurement of your source, it's the Fourier transform of that. And so essentially in this that combines the signal, you have the intensity that you would like, you have the intensity that you measure in your computer, and then you have the intensity that you would like to know, really your source, how it looks, mediated or convolved with the distance between the two telescopes. This U and V are position, I'll get back in a moment, in which your source C, the distance, your source C, the two telescopes that you are correlating here. So that makes your life, as you can imagine, more complicated. So you don't measure you don't take a picture like in the optical, you just take a picture, okay, there are some annoying cosmic rays, but to first order you have the image. Here you have the Fourier transform of the image. And not only, um, these were two telescopes combined, but then what do you do with two telescopes? You have one baseline, it's called baseline, the distance between the two telescopes, of a certain length. That can be kilometers, doesn't matter, but you have two. Apart from the poor sensitivity, it doesn't give you, because the idea behind this interferometer is that you play a trick. Instead of having one full dish, you have many part of the dish, and you spread, okay? But if you have only two dish, you cannot make a single dish. You can, but it's a bit poor single dish. So the more small telescope you have, the more your trick to fill a huge dish becomes real, and becomes also, and works better, as I show you in a moment. So what you should do, what you can do, there are two things you can do. Have a huge number of telescope. So n is the number of your telescope, and you can have, I don't know, ALMA is 60, 64, so, and the number of baseline that you can build and your correlator has to combine goes in this way, so it's a huge number. Okay, but then you have almost your huge dish filled with small dish and baseline. Or you can also, in combination with that, wait for the Earth to rotate, and then it's like your source see the distance of the two telescopes changing as it goes. And so it's like you pretend in this way to fill your huge dish. That's called So some people at the beginning manage just a few telescopes in a row, radio telescopes, small dish, put in a row, and wait 12 hours to fill the so-called UV space, that is this one. So you see every few minutes a signal is recorded, and then as the Earth rotates, you fill all this plane that in a way is your fake full dish. Okay, so in this case I could have built, in this particular case I could have built a 6 kilometer dish, single dish, impossible. Or I could have put 6 antenna in a row, like they did with the Australian compact array, and just observe for 12 hours a source. And then I fill this space, and in a way I have a dish filled, almost filled. There are gaps, but okay, nobody's perfect, so okay. So I'm not sure I managed to yeah, explain this trick that we use, but the combination of many telescopes and the Earth that rotate essentially produce many different distance between the pair of telescopes. And this different distance, in a way, they made up your large dish that you cannot build. So this is what we do. And it's very important this because in a way with the 5, 6, 10 telescope, even at many kilometers of distance, and if you are patient enough, 12 hours, you can actually recover a very nice radio image at high angular resolution. That is what we wanted to reach. Of course, the more telescope you have, the more sensitive you are. So there is more going on here, but okay, maybe you have to wait 24 hours. I don't know. So, okay, so let me show some examples. So this was the case. This was the case of 6 telescope that I'll show you later. Actually, the telescope that produced this 6 antennas put in a row of 6 kilometers and waiting, observing for 12 hours, and slowly building this because the Earth is rotating. If you have a larger budget, you can have your telescope spread, not in a row, but spread in the middle of a desert. This is the JVLA, probably the most famous radio telescope. I'll show you also in a moment this. So there are 27 antennas spread over 3 arms. And so these 3 arms help in speeding up the so-called UV coverage. So because they are not in a row, they are in a Y distribution. So you can more easily fill your UV space. Pity that you need 27 telescopes, so you need to have the budget for this, but okay. So this is a UV coverage of this telescope, the JVLA, where every telescope observes just for a few minutes. And this that you see here is the Fourier transform of what you have recorded here. Of course, there is an amplitude associated to each point. It's not just a point, there is an intensity. But so if you do the Fourier transform, this is a pretty low quality radio image, but still you see some sources already. After a few minutes of observation, that's really cool. But you can also observe longer. You can observe for 2 hours, and then you see the point that were here is each pair of telescope moved as the Earth rotates, and now you have many more circle-like because they've been tracking for 2 hours. So your UV space, your fake single dish telescope, is much better reproduced. This looks almost like a real telescope, and this is the corresponding image that is better than the one before. I mean, this is very noisy, and then the source here are appearing much better. It's clear what you detect. Also because of sensitivity. If you get enough time from the time allocation committee, you can observe for 4 hours with the same telescope. And now you see, you really feel all your your UV space. That means you fill your telescope, that in this case is about 27 kilometers in diameter. These are really spread radio telescope, so they can really reach a very high angular resolution. So you have here built in 4 hours with 27 antenna, almost a fake huge single dish of 27 about kilometer. And if you do the Fourier transform of this is your image now. So it looks almost real, no? It's not very exciting. There are 4 point sources, but this is what you get. It's getting better and better. So so this is the trick we use, and every radio interferometer uses. So not the single dish, the interferometer used to build radio image. And this is the Fourier transform that you do. Your nice package will do for you. So there are radio package that do all this calculation. You don't have to do for each pair of telescope. But the shape of the sources here is still a bit funny. It's stars-like. And this is effect of the fact that you haven't really filled your space. There are still gaps. So there are a number of tricks to compensate for this that I really don't have time because otherwise you would fall asleep. But okay, but so there are really packages that do this. It's called the cleaning process, and is part of what we do to get an image, as I will show you in a moment. So I don't dare to ask, but is anything, because this is was a bit dense, maybe it was all clear to you, that would be great. But if you have any question before I proceed, otherwise I proceed. It's okay, yeah? Okay. So, okay, so why do you do all this? You wonder, eh? So now my task is to convince you that it's worth the trouble. But let me first give you some general information. So what you do with your radio image, as I mentioned before, you do essentially 2 main things. This, as we will see, this is a typical, sort of typical spectrum that you will see at the radio frequency, so-called power law, and we will get to that later on, or maybe tomorrow. But you can detect this emission, the continuum emission, that is telling you about star formation. So it's not only AGN, because stars are also emitting in radio. So you can measure the star formation rate from this measurement. You can study the extended emission and study the AGN, as you will see, jet, lobes, and all this. But you can also have emission line or absorption line, for that matter. We have both. H1, that is really the classic at radio frequency, but also the same type of observation are also all the molecules that, for example, ALMA does. Because some people think ALMA is not really a radio telescope, but actually is a radio telescope. It's an interferometer with 64 antenna, a correlator, and all the Fourier transform that go with that. So I'm afraid it's a radio telescope. So and you can study the spectral index. As you will see, it's very important for understanding the mechanism that is going on. You can study from the line all the rotation, all the things that you do with gas, rotation, merger, all this funny thing, dark matter also. And the polarization that I will not get into because it's an entire universe out there, but this emission is very often polarized, so you can study all the properties of that. And so if you do all the effort, what you get typically in your radio observation, and we will get toward the end also to the fact that in many cases you get already done for you this kind of product. you can get an image, like I showed you before, just a continuum image. You have one frequency and you have one image. And you measure the flux, you do what you want with that, you see the structure of the sources, you do many things. Or you get, and this is more and more common in the new telescope, radio telescope, you get data cubes, a bit like the IFU. Yeah, we have done this for ages, so the IFU is the new one, but okay. So you get the data cubes where every channel corresponds to a frequency and so a velocity of your emission or absorption in this case, because it was the easy that I could find. So your observation, um, if you think about radio emission, or you would like to know something about the radio of your favorite object, um, important part is, first of all, whether you want to know about the continuum emission or the line emission, and this both give you completely different information, of course, about your object, about the emission mechanism, about all this. Is like in the optical, but just to show that in a way the thinking is very similar. You need to know which frequency you want to observe, because as I'll show you in a moment, different radio telescopes observe a different frequency for various reasons. Very often due to the location where they are or the structure that they have. The more high frequency you want to go, the better you should make your dish. So the more expensive they become. And the noise that you want to reach depends what kind of observation you want to know. But very important is, of course, the angular resolution, because different interferometer, given that we have this complicated structure of a correlator and all this, different interferometer can reach different angular resolution. So it's not like the optical that you say, okay, I'm going to a nice site because there I can reach a thing of, I don't know, 0.5. Here, every telescope in a way, almost every telescope, can reach a certain angular resolution depending on the layout of the instrument and the frequency at which this instrument works. Combination of these two. So you have many possibilities, apart from, of course, hemisphere, and then you are stuck, but okay. And another thing that I want to mention, and this is really our pain now, the situation of radio frequency interference, because it's all nice to have a mobile phone, it's wonderful, and internet and whatever, but all these satellites that are up flying and they communicate down, or the flight that brought me here or whatever, they mess up the signal that is much fainter that we want to detect. So some frequency are completely wiped out by this RFI, and we are really in a difficult situation. I mean, it's getting more and more complicated. The positive side is that with the radio you can observe day and night. That's cool. Huh? So in some cases you want to observe at night because of solar, the sun affect also radio observation, but in principle we don't care if it is day. The radio emission is radio emission, so that's nice, gives more possibility. Okay, so and then what do we want to see? So Christine already showed these two images of the galaxy. So this is an older image of the galaxy with the galactic plane. You see here some extragalactic object. This is Centaurus A. It's the largest and brightest extragalactic object that we see. And these are the new Meerkat image of the galactic plane with all the supernova, you see, all the supernova remnants that are here. And this is the galactic center. So really, really spectacular, because with Meerkat you have a big interferometer, as you will see in a moment. But actually, what I will concentrate, not today, but in the coming lesson, are this kind of object that, as I show you Hercules A at the beginning, these are the radio galaxy that I want to focus on in the next lecture. And again, this is another radio galaxy. It's from a radio catalog 3C31. And again, here you have the optical image, optical counterpart. So the black hole that gave birth at this big structure that is almost a megaparsec in size. It really can really be huge, and is overlay also with X-ray emission around this. So these are the ones that in particular we want to study, that are really a spectacular object, inside or outside cluster, but I will also show some more modest kind of object. So in the second part of this talk, I would like to give you some idea of how we make this observation, what kind of telescope you could use, we use and you could use. And I would like to finish off then with also a list of survey that are being done. Because you can say, and I would understand, why should I bother to go through all this? The proposal, learning about the proposal, what to propose, which depth, and then handle the data. But there is more and more out there, stuff already available that can be used. Maybe it's not all public, but it's becoming public. And so maybe for you, for your project, this is already interesting enough. So it's good to be aware of what is going on, because then you can get without much effort. Then you have to do your science, but that's okay. So these terrible acronyms are some of the radio telescopes that are available out there, some older than others. These are these are all interferometers with connected element, meaning that the two antenna pair of antenna are really connected. For example, nowadays used to be with cable, now with optical fiber. But so they are at most, yeah, 10, 20, 30 kilometer in the antenna spread over, let's say, 30 kilometer at most. And so these are, in a way, also the easier one to handle the data. But you see, there are many. I wanted to show some picture of them, something light, so you can follow. All these are in or they tend to be in very remote place. I don't know if you know some of them. The worst one is probably our telescope that is now has been just closed. That is Westerbork telescope. That is in the middle of the Netherlands. Well, actually no. For Netherlands standard is in a very empty region. But for Netherlands standard, so it's actually has all the flight to Schiphol and from Schiphol passing over. But so and you can see from the signal that there are many mobile phones around and all this. But okay, let me show some picture. So this is the Westerbork telescope I was telling you about. It's 14 antennas, all in a row. You see, they are all really east-west. No discussion about that. And this is the compact array, Australian compact array, so the other hemisphere. That's good, very handy. Few kilometers in size, east-west. So these are telescopes that they have to observe at least for 12 hours to build the fake dish, let's say, to reproduce the fake dish that you want to have. And they are a few kilometers in size. So the angular resolution that they can reach is not extreme, but is interesting. A compact array works up to 20 gigahertz, so can reach a second or super second resolution. few more telescopes that instead are sparse array. So this clearly have more dishes, so you can quickly build your fake big telescope. This is the VLA. This is, I'm sure you know about this, or many of you know. It's in the middle of the desert in New Mexico. And this Y shape that I showed you before, where we were trying to build the UV in a few hours, the UV space. This is the GMRT that goes to much lower. So this goes to from one main thing goes from 1.4 gigahertz up to 20, 25 gigahertz, while the GMRT goes from 1.4 down toward the megahertz, 200, 300 megahertz. So these two telescopes, in a way, are complementary. If you want to build a nice spectral energy distribution of your object, these two have a little overlap. And if you see here, this looks essentially transparent, but in fact, this dish are made by a net of metal net. So because it works at low frequency, so long wavelength of a meter or many tens of centimeter, doesn't matter that for the wave, this is a filled dish because you work at low frequency, at low wavelength, at long wavelength. So the dish doesn't see the wave, the incoming radiation doesn't see that there are holes in the dish because it's such a long wavelength. While this dish, I really feel, this is Meerkat that works, the one that of the image that I showed you before of our galaxy. These are nice dish, very polished because they have to go to higher frequency, so shorter wavelength, so your radiation should not see that there are holes. And they also have a different system of the secondary is a new construction. I can talk for hours, so I'll skip this. But this is the so this is new. These are relative. This is quite old, but has been refurbished recently, so gives a lot of new possibility. This is also quite old. These two are the new generation of radio telescopes, so you should keep an eye on them because these are the ones that give the new possibility. This is ASCAP in Australia, and is also a new interferometer in the middle, really in the middle of nowhere, of Western Australia. So this is ALMA that works at even higher frequency. So this dish become almost like an optical dish, not quite, but they have to be really well polished. And as you know, this is at 5,000 meter because it goes so high frequency that really otherwise the atmosphere would absorb and disturb a part of the signal. So this is in this plateau at 5,000 meter, beautiful spot, and has 60 antenna. So it's really one of the best telescope at the moment. But then I wanted to show you also something else, because I told you about the antenna and the radar and all this. But actually, in the past year, especially for the observation at low frequency, we got to a completely different design that is also a much cheaper kind of construction. So this is a LOFAR. I will show you something better in a moment. That works instead at meter wave, so 150 megahertz or 60 megahertz, so really low frequency. And this is the equivalent, let's say, in the southern hemisphere, is the Murchison in Western Australia. So this telescope go to so low frequency that they could essentially get rid of the dish and just build a dipole. And that's it. The dipole that gets the radiation and sent to the correlator. For this telescope that looks so nothing, the the main complication is the network of fiber optical to connect all the dipoles that are millions. So it's really a big computer that you have behind this. And for the LOFAR, is actually, this is in the Netherlands, in the north of the Netherlands, as you can see from the water that is around. But actually there are stations spread all over Europe. It's becoming a large network. I'll show you a little bit more in a moment. Actually, no, I show you a movie that was the source of all trouble. So this is a flyover LOFAR. So there are two types of telescope, of dipole, as you will see. This one is the high frequency, and this stick here are the low frequency. So, whoops, that went very fast. So this one, under this black stuff, there is a receiver, and that's it. And this little stick have a dipole on the top, and that's it. And so actually, if you don't pay attention, in no time you get all the grass and stuff growing around it, and you will not see anymore because they are just high. The stick are this high. So very, very unimpressive telescope, but a telescope that, because of the connection to so many dipoles, spread such a large area, is about 80 kilometers in the Netherlands, can reach still high angular resolution. So can reach the 6 arc-second resolution that before was only possible at high frequency. But really cheap construction, except for the fiber optic and the correlator that goes with it. Okay, let me finish by saying also that there are not only connected telescopes, there are also, because we are never happy as astronomers, correct? So there are also very long baseline telescope that, well, I'm sure you have heard with this Event Horizon telescope, but it's already many, many years that there are telescopes spread all over different countries, so many hundreds of kilometers, thousands of kilometers distance from one to the other. So you cannot connect them anymore with a fiber optical. So you record the signal, you send to a correlator that is in another place that should line up the signal and combine. So these are the VLBI. The VLBI telescope, there are a few. There is one in Europe. There is the VLBA in US, close to the VLA, similar, run by the similar institution. And the Event Horizon telescope was really put together in a way, combining everything they could to make this super high angular resolution. So you see, you really need the entire Earth. Actually, there's been for a little bit also a radio telescope on a satellite. There was a radio Astron from the Russian, and would correlate the signal that would record with the antenna on the ground. And that could reach, again, very, very high angular resolution. Okay, so actually for LOFAR, we have also, as I told you, apart from the Dutch array that is all in the Netherlands, we have all these antennas far away. And this means that by making an image with this far away station, you can go from image of this type to image of this type. So you see how much it change your understanding of radio source by going to high spatial resolution. Of course, you can miss out something, but that we will see another time. Okay. What do I have? Yeah, well, we as a radio astronomer, we are really, the big project is really the square kilometer array. And so the two telescopes that I showed you before, two of the many telescopes that I showed you before, Meerkat and low frequency telescope in Australia, are the two prototype, if you want, to learn how to get bigger and bigger. And this is the square kilometer array that will be even larger. Again, in two places, that is South Africa and Australia, because they could not decide about one place only, so okay. Politically, as you can imagine, that's an interesting kind of game. Um, but is in the construction phase, so is a big thing that is going to happen in the coming year. And actually, many countries also in Africa, and this I think is one of the most interesting spin-off of this project, got involved, and they are now refurbish telecommunication antenna, a bit like we did at the beginning of radio astronomy, to include those antenna in SKA to make the long baseline. I think this is a very nice, very difficult in practice, but very nice part of the SKA project that is evolving. So, well, I think I have I don't know what I have. I had a question, but okay. Let's skip the question because we are almost at the end. I wanted to tell you something. So I probably I scare you away maybe with the technique and with the complication of getting a radio image, but actually we are in a period in which for new people, certainly young people, there are a lot of possibilities, and there are more radio surveys that are becoming available, because some of these new radio telescopes have also a large field of view. If you want, I can again talk for hours about that, but large field of view, so they can do in a relatively short time the survey of the sky, north or south, whatever. And because they are so complicated, so time consuming, so also the size of the data set so large, essentially the pipeline to reduce the data become part of the experiment. I mean, you don't have only all this data dump in a disk, but you have the final product after the pipeline has run for this project. And so this is the new thing in radio astronomy. It took many, many years, but now it's really coming. And so I wanted to give you the list of this survey that are available, probably incomplete, but this is really something that you should pay attention to, because then you don't have to go to the trouble to make your Fourier transform or whatever. And there are also nice archives. The one of ALMA is really impressive. You get the final product, whether it's a cube or a continuum image. And so you really should, and it's growing, of course, as more and more observations are done, it's growing. So, and the VLA is also going in this direction, essentially to provide, I think it's still in the initial phase, but provide some pipeline. If you ask if you find an observation done by other that was interesting for you, you could also include in a pipeline and get the final product. So there are possibilities. So I've just listed here, and I mean I don't have to really discuss, but if you are interested, please. So there are a survey. Of course, many of them are also available if you go to NED or Skyview or whatever. But there are some classical surveys that are the typical, really the only one that were available so far, the MVSS and FIRST, that I'm sure many of you know, are 1.4 gigahertz from the VLA, done many years ago. But now there is their sister, the VLSS, that is at higher frequency, higher resolution. So for what I told you, to build a spectral energy distribution, you need more frequency. So that's a nice addition to this. But there are also other surveys that are available, or they are coming online, and there are some link here. But I wanted to mention the LOFAR survey that we are doing, because these are quite in advanced stage. And so the LOFAR survey, because it has such a large field of view, LOFAR can quickly scan the sky. The most complicated part is to reduce the data, but okay, Tim Shimwell is taking care of that, and big team. So, but the data, they are building up the northern sky, because LOFAR is a northern, of course, instrument. And there are data release, and the second data release is already available. So these are 6 second resolution image at 150 megahertz, and so you can look at them and you can see check whether your favorite object is there. And a few more survey are appearing or just available. For the one that care about the H1 or the line stuff, the situation is not so good because it's more complicated, because there are fewer telescopes doing, and so there are only single dish or the one with interferometer are really coming just now. It's a really big job to do this. But and as I mentioned, the ALM archive. So I just listed few. You can look in the PDF later on. So how much do I have? 1 minute. Whoa, 5 minutes. Okay. So so I just wanted to give you the example of LOFAR, just to see a practical example of thing that you can get. So this is a small part of the sky, probably I don't remember, 10 by 10 degrees, no, or less, a couple of degrees in size, and this is how this part of the sky, clearly away from the galactic disk, would look with all these nice sources in it. And so this kind of sources is what is available. This kind of information is what is available in the data release. So essentially, if you go to this site, you put the coordinate of your object. If you are lucky, you get an image of this type. If you are unlucky, they still have to observe or process, but will come. So, of course, this is the radio part. You will have, but as all the coordinates, so you can quickly compare to your optical image, X-ray image, whatever you have. And so, well, that's the radio sky. But one thing that I really, this is my last slide, that I wanted to stress. So we are having all this survey, is wonderful. These are million and million of radio sources that you have. What do you do with that? So if you have my age, you pick a couple of them and you study and you enjoy, and that's it. But the young people, they really like huge sample, and this is what we are doing, we are going through. And so a lot of emphasis, and I mentioned because maybe there are people interested also in this kind of thing, a lot of emphasis goes in the automatic classification and automatic, not only selection, but also classification. Radio sources tend to have a funny shape, as you have seen in some example. So how to classify, this is a source with a large jet, a small jet, curved jet, whatever. And so there is a lot of machine learning stuff done, and to try to automatically classify these sources. This is an example of a project that we had not so long ago on the self-organized map. There is a nice website. Do you think it will get? No, it doesn't get to the website. That's a pity. But you can enjoy that. So there is a nice website that actually goes to this. I try and work, but okay. It goes to this matrix of different objects found in 400 square degrees of sky, extracted and classified automatically. And then you can each box shows the prototype object, and then if you click on that, you will see all the objects that resemble to this, and you can also go to the part of the sky where this object was. I thought it was fun to look, but it doesn't work. Anyway, there is a major effort in doing this, and so that's another side of radio astronomy that is becoming more and more relevant, because yeah, we have so much that there are not enough PhD students to classify sources, so you really need to go to the automatic part. Okay, so that was my story. I hope I I didn't scare you away completely. There is, I think the radio emission can give you an interesting extra information about your object. There are many radio telescopes available, and although it's not straightforward to handle the data, but there are experts around, so um, still there are also many radio catalog and radio image. Please look at the radio image, don't take only the catalog. Um, that can be interesting for you, so keep an eye on them and don't push the radio aside just because it's too complicated or you don't know where to start. Okay, and that was my story. Yeah.
Thank you very much. Thank you very much, Raffaella. Questions?
Um, Thank you. First of all, thank you for this amazing lecture. This is Tuğçe Adınpınar, participants from Turkey. So I'm a big fan of radio astronomy. Also, I work on before as a radioman and radarman.
Oh, okay, good.
Actually, I don't have a question, but I would like to ask your opinion about one project. Actually, you mentioned about sun's radio noise. Also, you mentioned about importance of high altitude observation in radio astronomy. So, actually, my question about one project from NASA. This name is LCRT from Lunar Crater Telescope from far side of the moon, as you know.
Yeah.
And actually, this is 42 foot, approximately 13 meters diameter plan for ultra long wavelength. So actually, I'm wondering your precious opinions and your sights about that project. Thank you.
Well, okay. is very. So I will not see that project. I'm sure I will not see that project. I'm too old for that. I mean, it's a so challenging project that I don't know. Yeah, unless NASA and some other reason and other big um, organization will put a lot of money in it. Already to build the SK, we went through so many trouble. We are getting through so many trouble. Budget is one of them, and that I know that there is an effort, and I know some people are very much interested, but at the moment mainly on the technical side. So for the science, it's still stretch. Of course, with the radio interference, that will be the future. Yeah, I agree. But to get to comparable sensitivity and I don't know. I don't know where they will find the money. But the technical part is really impressive, and maybe we should push for that, at least for that. Okay.
More questions?
Hello.
Hi.
About the low far, I was curious with all these sticks and the dipoles. The complications are bigger or smaller than handling the data from the antennas?
Uh, on the complication, uh, I think the main complication is the ionosphere actually. So is the disturbance from this part of the atmosphere, the ionosphere, that disturb the signal. That has been the main complication to obtain a good image. So essentially, from one antenna, from one station to the other, there were already distortion. There are already distortion in the image. that would mess up the image. So actually the main complication was that. And that will not be solved by changing the structure of the telescope. Um, to be honest, the main reason to build in this way was also budget, because it's a very cheap way to build the infrastructure. The main budget went into the computer that had to take care of the data. That is huge. So I think that they can do better, and there is a lot of study for SK to see whether there is a design for the telescope, so the stick or whatever else, um, that can improve based on the experience of LOFA. So it's not the ultimate design. There is room for improvement. I'm not sure the dish, because the dishes they just become too expensive. You have a million of them that you have to put on the ground. It's just too much.
More questions? Because I have some.
Okay.
You made.
There is a question.
I didn't see you. Sorry.
Thanks. Just a couple of questions. One related to the synthesis. If the source is variable, if it affects anyhow, and also for the fiber that you told us that it's complicated, the fiber connecting the LOFAR stations. Are they dedicated, or what's happening there?
What is happening there? Yeah. So the first one is the variability. Well, the variability is, fortunately, they don't vary so much, the radio source. But well, some of them they do, and then it becomes a complication. Then this trick of, well, you have to do very short observation, otherwise your image becomes a mess. Actually, there are sources that vary very quickly, and you can spot them because of certain pattern in the image that you produce, because your standard procedure doesn't work anymore, so you start seeing some funny pattern. So, but if if you want to study variable source, you have to dream up a different approach. And for the fiber, so the origin of LOFAR was exactly to get the budget from the minister and all this, was to sell it as a telescope that would be partly doing useless universe study. I mean, they don't bring money, and in the Netherlands they really care about the money. But part was doing practical thing like agricultural monitoring. So the structure of the fiber became a very important network to do certain type of study parallel to the astronomy. So has created a huge network that both private people, I mean, improved the network for the Netherlands, but also for other research. That would be, yeah, sensor, whatever you need a sensor for, agriculture, water, earthquake, I don't know, whatever, lightning. So it's been sold also in this way. So the fiber network actually has become an important part that useful, and well, no problem to build that. The correlator, the place, because some combination of the signal happens already in the field. So there are essentially big computer in the field that combine the signal from all these stick, and then they send to a correlator in Groningen that combines all the station again. So those computers, those are the expensive, really expensive one.
I have one question. The list of radio telescope that you showed, these have open sky policies, or I mean, if a Brazilian astronomer wants to apply for time, they can apply for that,
Yeah, I think
or it need to be part of the collaboration or
yeah,
something
no,
like that.
I think which one I show you? I think they are all. Whoops. This one are all open sky facility. The SK we don't know yet. That's politics center in a way that was not common in radio astronomy, I have to say. Radio astronomy is pretty much open sky. Anyway, so few people can reduce the data that who cares about all the rest, so I don't know, but what has been always open sky. SK, because they are intergovernmental organization, some may request participation, but and Alma is open sky. Alma is open, yeah. So no, they're all open sky.
And also, you showed at the beginning an image of the continuum and an emission line, but it means usually the radio telescope works in a single frequency.
Yeah.
So if I want to build a continuum image, I have to take at least two or three different frequencies.
You build a continuum image at a certain frequency. So you build a continuum image, like if you look at the one of LOFAR that I show you. This is an image at 150 megahertz.
Yes,
That's
yes.
it.
But
One frequency.
yes, one
If
frequency.
you want to build the spectral energy distribution, then you need the 1.4,
Different
the
frequencies.
5, yeah.
Ah, okay.
So the image, the continuum image, usually you get one frequency or multiple frequency if your goal is really to sample the spectral energy distribution. Depends on the project. Yeah.
Depends on the project.
Mm.
Oh, okay. So, more questions? If not, let's go to thanks Rafael again for
Thank
the
you.
excellent talk.